Welcome to my classroom. So in this chemical process calculation course, we have completed one module on unit conversions and we have started the second module, material balance. Basic principles have been covered in the previous lecture. So material balance in unit operation without chemical reactions. And at steady state, there are various unit operations like crystallization. In the previous lecture, we have discussed in detail about the principle of crystallization, the advantages of crystallization, and in this lecture we are going to discuss about material balance in evaporators, dryers, distillation units, mixing, all the various unit operations. Okay, get ready. I hope you have completed the previous lecture in which we have discussed about material balance, what are the guidelines for doing material balance, and we have seen the classification of material balance, right? So material balance can be classified into two, that is material balance for the cases where there is no chemical reaction is involved, without chemical reaction, and the second case is with chemical reaction. And both this with chemical reaction as well as the without chemical reaction can be classified into two further, that is steady state and unsteady state operations. So for without chemical reaction also we have steady state, unsteady state, and similarly for with chemical reaction, steady state, unsteady state. Okay, so here steady refers to the parameters changing with respect to time. Okay, and we have also seen there are what are the examples for material balance without chemical reactions, that is for unit operations. I have discussed about crystallization in detail. So we have crystallization, evaporation, absorption, distillation, drying, and extraction. So these are some of the unit operations we are going to do material balance, right? So in crystallization we have seen various parameters like what is crystallization. So it is a process in which the solid particles are formed from a homogeneous phase, right? So during crystallization process, the crystals form from a saturated solution, and the mixture of these crystals as well as the associated mother liquor is together called as magma. So we have to know what is magma. The combination, the mix, the both together, which are together, the crystal formed as well as the mother liquor, both together are called as magma. And we are going to separate out the crystal, and what is coming out is mother liquor. Okay, so that's what happens in a crystallization. We have seen why crystallization is considered to be one of the unit operations, preferred unit operation for separating out the pollen. The products formed are uniform in shape and size. Okay, so that way, to get products of uniform shape and size, we prefer this crystal formation, and it is easier to separate out the crystals from the mother liquor, so that way ease of filtering and washing it, and we can use it further, right? So that way, and it is high purity, the crystal forms are of high purity and they don't crumble easily also, right? So that way we have seen, and also we have seen supersaturation is to be obtained, because the crystallization will happen, that is first nucleation and growth phase, these two will happen only when there is saturation, supersaturation in the system. We have seen it can be affected by a few different methods. One is by reducing the solvent, the amount of solvent in the present in the system. That is how to separate out solvents out. It can be evaporated out. So by evaporating the solvent out of the system, we can do bring in supersaturation, thereby we can affect crystallization taking place. Another way is by cooling. For example, by cooling to lower temperature, water can be turned into ice, which we discussed in detail. And we have seen in two other methods called introducing a third component or introducing a third solvent, which will can take place by salting or precipitation. This crystallization will occur, right? We have seen the material balance for crystallization. What will happen, there will be one input, that is feed entering the system. Feed will contain the solute as well as solvent, and evaporation of the solvent takes place, but the solvent getting evaporated will not contain, we will assume that it is not taking away in any of the solute along with it. So therefore the concentration of solute present in the vapor stream will be zero, right? And there are two more product streams. One is like crystal formed. So we are considering it to be high purity. That means the amount of solvent present in the system will be zero in that. So that way we get pure crystals. and the last one is thick liquor, right? So the mother liquor we are going to get. So that mother liquor is collected. Mother liquor will be having the solute as well as little amount of solvent. Okay, so solvent will be more, solute will be medium, because some of the solute present in the feed has been precipitated out or taken out in the form of crystals. So that way there will be less concentration of solute present in the mother liquor. Okay, so that's what we have seen. We have written the overall material balance, and we have seen we can write one overall material balance, one solute material balance, and one solvent material balance. Okay, so the one input, three output are present in this system. Okay, and we have seen the some of the guidelines to be formed, right? So we have seen various guidelines which are to be formed. So, and we have seen what is the overall material balance according to law of conservation of mass. As I said, it is a mathematical representation of law of conservation of mass. So we have material input minus material output plus material generation within the system minus material consumed within the system is equal to accumulation of material within the system. And I told you about the steady state means what will happen to the accumulation term. If it is steady state, accumulation will be 0, so that term will become 0, in the right hand side is equal to 0. And if you are considering a system without unit operations, if you are considering unit operation where there is no chemical reaction is involved, then material generation term will be 0, material consumed term, that is the disappearance, the rate at which it is disappearing also will be 0. Hence we are left with only two terms in the left hand side, that is material input minus material output equal to 0. If you take it to the right hand side, we have material input is equal to material output. So that is a simplified material balance equation for material balance without chemical reaction at steady state. Okay, so we have seen that one, input minus output equal to 0 for steady state. If it is unsteady state, material balance equation will be input minus output equal to accumulation, because we are considering the case of without chemical reactions. Okay, so steps for material balance problem. So if material balance problem is given, so what are the steps that we have to follow? I am telling you so that you can practice the problem set which we are going to circulate. Okay, so whatever problem set problem you can take out to any textbooks, exercise problems, example problem, or previous year question papers from various universities. You can try to solve the problems on material balance without chemical reaction at steady state. Okay, so first step is, for any problem what we should do is first read the entire problem completely and meticulously. Carefully you read all the throughout the problem, so that one or two times if you read, you will come to understand and visualize it, and we will be able to make a block diagram of the system. It's block diagram, we need not draw a exact unit operation. Like if it is distillation, you need not draw a distillation column. If it is crystallization or dryer, you need not draw an entire picture of crystallizer or dryer. Okay, what we have to do is we are making a block diagram. We will just make a box or a rectangle or a circular shape, whatever way. You just make a round and marks, and that is our system, right? That this system is crystallizer or this system is distillation. Then you identify from the problem how many feed are there, how many exit streams are there, inlet stream, outlet streams, feed, products, byproducts, okay, vapors. So whatever is there, we have to identify and draw them. And also by reading the problem, we will label the flow of each stream. As I said, input stream, output stream, either any recycle is there, we have to draw that recycle stream. Okay, associated composition also from the given data. You can write down the associated composition, like what is the mole fraction of A solute in the feed, what is the mole fraction of this in that one, like that we can check. Okay, so once we have written down the given data and whatever is given, like mole fractions are given, once you have plotted them, so then we can also determine the associated composition. Like if we know A, we can find out what is the component amount of B as required. Okay, if required, we have to determine. So we will write what is the associated B component. If this much is entering, what is the amount that is present in the product. Like that we can determine the associated compositions also. And for doing that and all, we should establish, by doing so we will come to know what is the tie component or tie element or key component or key element. We have defined what is key element in the previous lecture, please refer to it also. This is the one which is having minimum input and minimum output. Let me say one input, one output, and it doesn't take part into the any changes in the system. If it is like that, it will be most preferred. Okay, and after doing all these things, after reading the problem carefully and drawing a block diagram, noting down the feed inlet stream and outlet streams, all that, after noting down the composition, now we have to go for choosing a basis. How to choose a basis also, it is discussed in detail in the previous lecture in the guidelines of material balance. Okay, in the guidelines of material balance, we have seen that if it is a reaction, chemical reaction is involved, we have to go for mole basis. If no chemical reaction is involved, we should go for mass basis. Or for gaseous streams, we should go for mole basis. For liquid stream and solid stream, we should go for mass basis. And if it is specifically asked in the problem, we can go for even time interval as the basis, that we have to choose a basis. Then we have to write down the what is the overall material balance, and for each component material balance we have to write material balance equation, and we have to write individual material balance equations also. And we have seen that verify that what is the degrees of freedom. Okay, that is, it should be 0, right? Number of unknowns, number of equations involved. So that independent equation, number of independent equations and number of unknowns should be equal. The difference between number of unknowns minus number of equations is equal to 0 means degrees of freedom is 0. We can proceed to solve the material balance problem, right? If there are more unknowns, less equations, we cannot determine the solution for it. And if more equations are there, less unknowns are there, we have to judicially, we have to take, it is our own judgment to take out to which equations, set of equations to make use of. We have seen that the most predominantly present component, whichever equation representing predominantly present components, that equation should be preferred, right? And we have to, once we have this thing, we can solve the problem. Then it is like mathematics. Two equations are given, find the xy value. Three equations are given, find xyz value. Like that we have to do mathematics, whatever by simplification, simultaneously solving that equations, we will be able to get the unknown parameters. Okay, but after finding the values also, again we have taken, initially we have assumed three equations, right? We have to substitute these values in those equation. Either it may be in overall material balance. If you are finding one of the overall how much kg or how much kg moles of stream is produced, you can plug it into overall material balance equation to verify it, or you can substitute in one of the individual material balance equation, like for, you may be writing for solute, or you might have written for solvent, or you might have written for inert substance, right? So we can plug in that these values calculated into those equations, and we can still determine and verify whether this what we have calculated is matching with the initial equations or not. Okay, and finally we have to write the answer in sentences. Make a sentence stating what the so and so parameter is calculated to be this, and don't forget to add the units to it. Okay, we should, after solving those given equations, after finding out the unknown parameters, we have to write the, sometimes we might have chosen a different basis than what is asked in the question. So in those cases, unit conversions, like we may be asked to find for 250 kg what is the thing, like that, but we might have assumed a basis of 100 and determine the value. So accordingly, proportionally, how much will be produced for the required quantity, all that we can determine. Okay, so then we have to write down the answer in sentence along with units. Write down with unit, don't forget to in the units. So always when you are writing a summary or inference or your own observation, what do you feel, that is better to, it will be much appreciated. Okay, you can say that this value is exactly correct, or you can say this value is a bit of error. Also you can cite why it is, we are not getting the correct answer, or why the value is too high or too low, why it is negative or why it is positive, like that. Whatever we are not able to identify, you can give the reasoning. Okay, logical reasoning you can try to provide. Say we have to, while doing all this exercise, we have to be clear that what are the terminologies that we are making use of. Okay, because usually when we say n number of components are there, we use A, B, C, D, capital A, capital B, capital C, capital D. These four are four. Let us assume a four component system. We can go for A, B, C, D as the components present in the system. Then what will be the mole fraction of them? We can write XA, XB, XC, XD. Okay, these four are the mole fractions of A, B, C and D respectively. For a two component system, what we will do is we will be writing for XA and XB, right? Means two components A and B are assumed. So in that case, XA and XB represent the mole fractions of A and B respectively. Okay, also we know that in those cases we will not be using that XB term, because we know XA plus XB equal to 1. So always once we you get the XA value, XB is always can be determined from XA, right? 1 minus XA is XB for a binary system. So that's why we don't write a material balance for B if you are writing a material balance for solute A, right? And overall material balance. So one overall material balance and one component material balance for solute A is sufficient. So in that case we can skip A. Why I am telling this A, B, C, D, all this thing is, when your multiple components are there, then you have to represent the X is mole fraction. Sure, for X in liquid phase we will use X as mole fraction, for gas phase we will use Y as mole fraction. Even in any course, mass transfer course also we are going to do the same. Okay, so in that case, when subscript X is term, in X subscript is A, B, C, D represents A component, B component, C component, D component, right? So that we should know. And it is present in, because XA is the mole fraction of solute, but what is its presence in feed? What is its the amount present in the vapor? What is the amount present in the mother liquor? What is the amount present in the product or in crystallization? What is the amount present in the crystal, right? So that mole fractions we have to differentiate them. So we will write XAF. If F is the feed, if capital F is the feed, then XF is the mole fraction of solute A in feed. If P is product, then XAP or simply XP is the mole fraction of A in product. And if B is byproduct, capital B is byproduct, then XB is, remember, that's why we should avoid B here. XB is mole fraction of A in byproduct. Why I am doing so? We are considering a two component system, so we are never going to write XB. Okay, so in those cases when I say byproduct, I can use XB, or you should say P1 P2, you can say XP1 XP2 to avoid confusion. When you are using the term XB, here we will get confused. So that way we should be clear what we are defining for assigning the subscripts to the mole fractions. Similarly, if W is waste, then you can say XW is the mole fraction of solute A in waste stream. If M is the mother liquor, then XM is the mole fraction of solute A in mother liquor. Okay, so like so one of the unit operations that is widely used in most of the industries are evaporation. Means thickening. We have to separate out the water at least present in the product, right? Some of the cases we have to wash them out, so we have to remove the water, right? So removal of moisture, if it is present in small amount water, we have to say it is moisture removal, which is like drying operations it is. But if it is a liquid solution, we had the products in liquid with water, all these things, we have to remove the water, excess water present in the system. Or as I say, we have seen crystallization, where it is to bring super saturation into the system. What we do, we try to evaporate out. One of the different, there are four ways that are there. So one of the ways to evaporating the solvent, right? So that way evaporation is one of the unit operation, industrial level unit operation, widely used in the industries. The main purpose will be like we have to concentrate the aqueous solution, because the product that is naturally obtained or something which can be extracted out from some of them, it may be more aqueous, that is a more diluted one. So but for packing and transporting, aqueous one is not needed. Once we have concentrated them, and while end use we can still dilute it again to make use of it. For example, juice is there. If we get a concentrated juice, then while making preparation we can even dilute 1:4 water, we can mix it and we can use them, right? So that way concentrating the aqueous solution is one of the uh, essential unit operation in the industries. So the vaporization of the solvent, mainly water, or removing it as a vapor is widely used. Okay, some of the example are, if you are considering sugarcane industry, in sugarcane industry the cane sugar juice is there, right? So to that it will be more diluted one, okay, because water will be present, so that water needs to be evaporated out. Concentrating the cane sugar juice is one of the example for this unit operation, evaporation unit operation. Another one is in fertilizer industries, ammonium sulfate will be obtained. Okay, so that in that also that concentrating of ammonium sulfate is being carried out in fertilizer industry. If you are joining any petrochemical industry, one of the byproducts of petrochemical industries are fertilizers. Okay, so essentially if you are going for industrial visit to some of the industry, you will see that one, this concentration of ammonium sulfate unit is present is in the fertilizer industry as well as petrochemical industries. Okay, also if you are looking at soap industry, okay, in soap industries glycerin is one of the product. Okay, so from the soap spent lye we have to concentrate out the glycerin. So for that purpose also this evaporation unit operation is performed. And we have seen that we have to remove the solvent by vaporizing it. How it will be vaporized? It needs to be heated. So based on the mode of heat we are supplying, either it can be directly fired. You have a vessel, like you are cooking. How we can cook? We can make rice in vessel. We can direct heating. Okay, that is, you keep the vessel below which you are firing the wood, right? So in that case you are directly heating it. That is one way of using that one. Indirect methods are there, like jacketed kettle can be there, where we will produce steam somewhere else. That steam will be passed on through the jacket out. Jacketed kettle means it is a two layered one. Inside vessel is there, outside you have another vessel, and that is sealed. The outside vessel will be sealed and the outside vessel will be heated using steam. So what happens? The heat transfer takes place between this steam, from steam to liquid present in the vessel. So the it is releasing the heat to the vessel, contents of the vessel. So steam gets condensed and it can be collected other way. Okay, so that essentially the steam heated evaporators are there. Direct firing or direct fire evaporators is present, and you can use jacketed evaporators or steam heated. So it is for batch operation, small scale operation, jacketed kettles are used, or jacketed evaporators are used. Whereas for high industrial application, for continuous operation, steam heated tubular evaporators are present. It is like heat exchangers are there, and long tube evaporators are there. Then in that also, based on either the liquid is flowing from top to bottom or bottom to top, we can call it as climbing film evaporator or falling film evaporator. So these are some of the classifications of evaporator which we are going to study in detail in heat transfer course. Okay, so essentially we have to make a diagram. In this course what we have to do is material balance through any type of evaporator. So what is the input? Our concern is what is the input, what is the output. So right, in this model we are concerned about material balance. In the next model, immediately after this mid exams, we are going to discuss about energy balance also. So we should know how much heat is entering the system, how much heat is leaving the system, how much meat is consumed, right? So that way heat balance also we are going to do, that is energy balance. But now currently we are concentrating on material balance, right? So if you are trying to make a diagram, so if you look at a diagram, we can see that it will have a feed stream. This, so we are having a diluted solution, that is feed. That feed will be having a certain amount of solute present in it. Let xf be the concentration of mole fraction of solute A in the feed, that is xf. So we have a stream F, capital F, kg per hour, because it is continuous operation, kg per hour, F kg per hour be the feed, and xf be the mole fraction of solute A present in the feed. And we are having two outputs here. One is, as we said, the solvent gets vaporized. The solvent gets vaporized out from the top of the column. So that way we have vapor stream leaving the one. So let capital V be V. Some textbook will use E, evaporated. Okay, so we can vapor or evaporated one. So we can use either V or E. So V, capital V kg per hour is the kg of vapor that is leaving the system. Okay, then what is left out at the bottom of the system is the once the solvent is removed, we have concentrated solution at the bottom. So that is called thick liquor. Thick liquor. So thick liquor is, you can represent it by T or L. So L kg per hour. So what are the concentration of solute present in the vapor? There is no solute present in the vapor. Okay. So that way the concentration of solute in the vapor is 0. And what about the concentration of solute in the mother liquor or thick liquor? Here it is very high than the feed. Mole fraction is going to be more because we have removed the solvent. So obviously this whatever XL, let XL be the concentration of solute in the thick liquor. So this is going to be greater than that in XF value. Always your XL value will be greater than XF value because we are removing the solvent. Okay. Then if you try to make a table out of it, table for this diagram, how many input streams are there, how many output streams are there for overall and for solute. Make a table. So write first column overall solute, second column we will write number of input, third column you will write number of output. So for overall, what is the number of input? There is one input in the system. How many outputs are there? Vapor and thick liquor. So there are two outputs in this system, one input to the system for overall. Similarly for solute, how many input, how many outputs are there? We have seen that in vapor is solute free vapor. So there is no vapor present in the, there is no solute present in the vapor stream. So number of input is 1 anyhow, but number of output is only 1 because solute is present only in the thick liquor. So the number of input for solute is 1, number of output for solute is 1. Okay. So in this diagram what are all there? We have a stream called F stream, feed stream, F kg per hour. We have a vapor stream, V kg per hour, and we have a thick liquor, L kg per hour. Okay, we are writing vapor 1 V1 and thicker L1 because in the next thing we are going to consider, because here the steam used is used only once. Here the vapor will be at high temperature, right? The whatever is the operating temperature, vapor will be leaving at the operating temperature. Let me say if we are operating the vapor at some 70 degrees Celsius, so the vapor will be leaving at 70 degree, but it has to be cooled down and it has to be sent out. Vapor, water vapor we are not going to use. So that way, if it is water, so that vapor, some amount of heat is there, no? So later what people thought is, why not we use this vapor to preheat the feed? So that way people moved from single effect evaporator to multiple effect evaporators. Okay, remember these things you are going to study in heat transfer course. Here I am giving you just a brief introduction. So in a case of a multiple effect evaporator, we can use this heat present in the vapor to heat the another stream, right? So that is the concept in multiple effect evaporators. So now we know how to draw a block diagram for an evaporator. We are going to make a box and write this is the evaporator. For evaporators there will be 3 streams, one inlet, 2 outlet streams. So we have a feed, we have vapor, and we have product, concentrated thick liquor or concentrated liquor solution, which can be the product. Okay, and we should use appropriate terms for it. Means to denote the symbol F stands for feed, V stands for vapor, thick liquor L. Okay, so we have previous thing, previous diagram we have seen that V1 L1 is used because in future we are going to discuss about multiple effect evaporator. So in those cases we are going to use V1, V2, V3 are the vapor formed from the stream 1, means single effect, first effect, second effect, third effect. Here effect stands for the number of units. Okay, multiple effect means many units are there. When I say 3 effect evaporator, there are 3 columns, 3 evaporators arranged in series, right? So that way we are going to see. So that's why we are writing here V1 and L1. So we can write now overall material balance and individual material balance. Try it. What is the overall material balance? F is equal to V1 plus L1. I hope there is no doubt about it, because it's overall amount of feed that is entering is F kg per hour. Vapor leaving is V1 kg per hour, and L1 is the thick liquor kg per hour, that is a concentrated product kg per hour flow rate. Okay, then we can write the individual material balance for solute, that is xf into f is equal to xl1 into L1. Okay, xf into f is equal to xl1 into L1. If you have tried to write what is xv into v, it is xv is equal to 0, because it is solute free vapor. So if in some numericals or some cases, let me say there is 1% solute A is present in it, so in that case we have to substitute that value also, but it is very rare. Okay, it's very rare. And regarding the streams, what is the thing, when 1 kg of stream is condensed, obviously we can expect 1 kg of vapor is produced. Okay, so cost of steam consumption is a major concern in the industries. Okay, when particularly this evaporator, because steam itself, you don't get steam freely, right? You should have a boiler unit where you have to produce steam, high pressure steam has to be produced. So that way, to reduce the cost of steam consumed in this, and to make use of the vapor that is present in the heat present in the vapor stream that is leaving the top of the column, people have come up with a good idea that multiple effect evaporators can be used. What is multiple effect evaporator? This is evaporators, n number of evaporators connected in series. Okay, so vapor produced in the first effect is used as the heating medium for the second effect. This is, for example, for forward feed forward feed in effect evaporator. You can say that vapor produced in the first effect is used as the heating medium in the second effect, and vapor produced from the second stream is used as the heating medium for the third effect. Like that, n minus, let me say there are n number of effect, n number of units are there, n minus 1 unit, the vapor coming out of the n minus 1 unit will be used as the heating medium for nth unit. Okay, so that is the forward feed n effect evaporator. But usually in industry they do it in other way. The vapor produced from the nth unit will be the heating medium for n minus 1th unit. So like that, we will coming down to the first 2 3, the vapor coming out of the third stream will be the feed to second stream, the vapor coming out of the second stream will be the heating medium for the first stream, and the capacity is same in all the evaporators. So it is assumed that the vapor produced in the each unit is same. So we can say V1, V2, V3 will be equal to summation of V1 plus V2 plus V3, overall V, what is that leaving. Okay, so instead of saying that V1 plus V2 plus V3, we can simply say 3 times. If it is a 3 effect evaporator, we can say the vapor leaving is equal to 3 times V. That is, vapor produced in 1 unit is V. The vapor produced in 3 units will be 3 times V. So that way, that will be the amount of vapor that is leaving the system. Depending upon n effect, there will be n times V. That will be the amount of vapor leaving the system in case of a multiple effect evaporator. But in multiple effect evaporator also, there is only one feed entry and there is only one concentrated liquid outlet. Okay, so that is what happens in this case. So this is there we have a overall material balance for a triple effect evaporator will be like F equal to V1 plus V2 plus V3, which can be even written as 3 times V. Okay, so F equal to, in a triple effect evaporator, the overall material balance will be F equal to 3 times V plus L1 or L3 if it is third 3 effect, no? So it should be L3. So whatever is L1 that is entering will be L2 and then L3 we are going to get finally. Obviously the concentration of solute in L1, L2 and L3 are going to be different. Okay, because stage by stage we are removing more solvent from the system. Okay, that is the overall material balance. We will do some numerical on these evaporators. One of the of another unit operation that is being used in industries are leaching. Leaching refers to extraction of one of the solids from a solids. Say for example a solid composite is there, we have to separate out for example mostly in the copper, aluminum, several materials are present in the its ore form, right? So in under the earth we get it as ore. So we have to leach out precious metals or this copper, magnesium, all this. So we have to do leaching operation on it. So leaching operation essentially is adding a liquid solvent and taking out the one of the constituent present in the solid mixture. So from a solid mixture, if you want to separate it one of the component from it, so we use a third component called solvent. So by introducing the solvent into the system, we are leaching out the solid component. It may be slowly diffusing out of it and getting into the bulk of the liquid. So that operation is called leaching. It is one of the industrial operation. It's being used in pharmaceutical industries, sugar industries and other industries. So the just a brief introduction to leaching process. Okay, leaching is an unit operation. Okay, some of the cases chemical reactions also will be involved. We are mostly without chemical reaction we are considering. So this has other names called, it's an age old process. It has been done for long time. Even before this chemical engineering things came into picture in our ancient world, they have already separated out the things to make all the weapons, right? So that way this leaching is one of the operation to separate out one of the solid constituent from a solid mixture. So separation of a solid from a solid is leaching. It has other names called lixiviation, decoction or elutriation. So elutriation is the term which we use when so that particular substance which needs to be separated out only present in the surface, by just washing off with the solvent we get that out. So in that case we call it as elutriation. Okay, and this is one of the major operation in metallurgical industries. So in our neighbor building we have metallurgy department, so where they study a lot about separation of various metals like aluminum, nickel, cobalt, manganese, sodium, uranium, all that, right? So they have to separate it from its ore. So where they perform leaching at large scale, because the large amount of these metals has to be separated out. So they do it at very large scale. So industrial level leaching is being performed. A small scale is like in small scale means we are taking tea and coffee. So they are also being leached out. Usually earlier days before this tea powder, people used to put the tea leaves into the hot water and extract the tea from it, right? So coffee seeds, from coffee seeds we have to take out the oil from groundnut oil, so tilka tel, whatever oil. So some see nowadays a lot of duplicates are there which are taken from petrochemical. One of the byproducts from petrochemical industry is some oil. Whatever essence you add to it, it becomes that oil. For example, if I add coconut flavor, it becomes coconut oil. When you add sunflower flavor, means when you put tilka tel flavor, it becomes tilka tel. So like that duplicate oils are there. We are not talking about that. We are extracting original oil from oil seeds or other roots. Even other thing, Ayurvedic medicines we take, we can extract out some of the medicines from the root. Are we right? So particularly during this COVID situation in Tamil Nadu, they distribute various extract soups which you can drink to take care of corona also. So that way this extraction of medicines from medicinal plants, okay, medicinal plants from roots or its leaves, so that is also leaching out. So leaching operation is carried out in it, and removal of tannin from tree barks are there. That is also one of the industrial large scale operation. Extraction of oil from, so some of the examples of unit operation leaching are metallurgical industry where they extract out aluminum, nickel, cobalt, manganese or like that, uranium like that. And extraction of sugar from sugar beet with the hot water is also a example for leaching operation. And extraction of oil from oil seeds, and we have to and other operations are like removal of tannin from various tree barks, preparation of tea and coffee, extraction of many pharmaceutical products from plants and plants roots, and leaves are examples for this one. Okay, but in this leaching operation, as it is like leaching is like diffusion of solute from the interior part of the solid to external part and into the bulk of the solution, right? So in this, surface preparation is very important, because when you have a large bulk of ore, the leaching, it has the diffusion, it has to travel a long distance to come out of it, right? So in those cases only your mechanical operation course is playing a role. We have to do crushing of those large sized solids into small sized solids. Leaching will be accelerated if you want to accelerate, because that the solute has to travel out, right? So that the solute has to travel from interior part of the solid to external surface and then get into the solution. So if you want to accelerate that, that size reduction is rather, either you can do crushing, other things also. Okay, so that way preparation of solids is very important. Proper preparation is must for enhancing the leaching. So because the smaller the size of the particle, quicker will be the leaching. That means more amount of solute will come out. So that way, smaller the size, more will be leaching. And we don't need this solid, means mechanical operation, that is crushing, all the size reduction is not required when the material which is to be leached out is present only on the over the surface. If it is over the surface, no need of this thing. Okay, no need of size reduction. Okay, it's like difference between adsorption and absorption. If it is only absorbed, it is absorbed all through it, then it is different, but only absorbed on the surface, it is different, right? Similar to that here, when the solute to be reached out is present only outside the surface, on the surface of the solid material, in that case no need of size reduction. But if it is present throughout the solid, in that case size reduction will enhance the leaching rate. Okay, leaching will be more. So hence the leaching is depends upon various parameters, like leaching depends upon the nature of the solid. If it is plant kind of thing, nature of the cell structures. Okay, so the leaching depends upon the nature of the solid or nature of the cell structure of the leaves or roots, whatever it is. And diffusion of solute from the material to the surface and into the bulk of the solution has to take place. So the rate at which diffusion is taking place, it is diffusing fastly in the solid, within the solid, and also within the liquid. So that also determine what will be the rate of leaching. And as I said, this particle size and its distribution is also important, because particle size also there will be range, right? In screening, in mechanical operation course you might have studied, when you are doing the crushing, we don't get uniform sized particle. We have to do sieving and we'll have a different micron size particles. So the distribution, major components are present in which sieve or which micron level, that will also play a role in this leaching operation. And another thing is the solvent which we are using, whether it is cheap or costly, or another thing is that solvent, how much the solute will be dissolving. So what is that? Solubility. Solubility of the solute in the given solvent also plays a role in this rate of leaching. And also the temperature of operation also will play a role in the rate at which the leaching is taking place. So this leaching can be carried out in different ways. One of the ways, like as I said, the ores are present below the earth. So what we can do is we can put two wells, one well and another well is there, one well for inlet, one well for outlet. In inlet well we pass the solvent into the earth, so below the where the ore is there, and that in the other outlet pipe, this whatever is leached out along with the solvent, the leached out metal will be coming out. By example for that is that copper is leached out in that fashion. In some places copper are present below the earth in its ore form. So in that cases, those when this inside too, it is called inside too, because where it is present, from there we are not taking it out as solid, because mining is a very tedious operation. I hope people coming from northeast and this Odisha, Jharkhand, all these places know how much pollution it causes, how many people die over these operations. We hope recently we studied about rat hole mining, right? It is like rat holes we make in the mountains and people go and work. If it rains or some landsliding is there, people die, and those people are not accounted, the owners are not accounted for it, right? So if you are arranging for a small meeting and somebody gets an accident, there will be FIR filed against you for your lethargicness of not taking care of your participants. But when this kind of corporate I think so. This is not concluded, but coming back to our subject, so this that's why in situ leaching is preferred for this copper, because that is easier, because easily we can extract out the solvent out of it. So example is copper leaching. Okay, and there is one called heap leaching. We have taken out from the earth, and where they are kept in a heap shape, and at the top of the heap we put a small, like people, some people heat na house, they eat rasam sambar like that. We make a heap of rice, and we make a well into it, small well into it, and we pour sambar rasam into it and mix it and eat, right? So like that, this heap leaching is like we have a heap of ore or whatever solid material that has to be from which we have to separate out the solute, and at the top the solvent is poured or sprinkled continuously, it will be flowing, or even the solvent may be filtered and again recirculated, that so that will, in that solvent also the solvent will get dissolved into it. Okay, so that is the example. Mainly this extraction of uranium is example for it. Gold is leached out like that, heap leaching. Okay, so another method is called percolation tanks. Like you have a ore material taken in the form of like filtration setup. No, you have gravels, like several layers of sand, several layers of gravels are kept in that one, filtration of water. So similar to that, percolation tanks consists of, you have several layers of this ore material and other packing stuffs are there, through which we will be passing the solvent and the leaching out will be taking place. Other type is like from seeds, oil seeds, what we are doing, we could extract out, right? So that extractors are there, filter press, we press the solid seeds to take out the oil out of it. So that is one type of leaching operation. Another one is like agitated vessel, by just mixing it we can take out this thing, the solids out of it. And there are some extractors like from plant extracts, from plant and oil roots, all these the medicinal things you might have seen. Some, we vaporize, a solvent is taken, these materials are added to it and we vaporize them and collect it, right? So like that, these extractors are present. Okay, there are several extractors like rotocol extractor, Kennedy extractor, Boltzmann extractor. So these are some of the most widely industrial scale, large scale applications of that one leaching operation. So in essentially in case of a leaching operation, there will be two input and two output. There will be two input and two output. So as usual, there will be one feed. Feed is the solid material. So if each contains some certain amount of solute and remaining are inert, we will say remaining are inert. You have a feed, then what is the other input? There are two inputs I said. So one is feed, another one is solvent input. So we have solvent input, solvent kg, S kg. Let us say F is the feed, S is the solvent. We have F plus S is the material input. So it's a steady state operation, no chemical reaction involved. Input should be equal to output. There are two exit streams, or there are two outputs in the system. One is overflow, another one is underflow. Underflow is the leached out solids, leached solid. Overflow is the solution. Okay, so that way we have overflow and underflow. So in a leaching unit, if you want to make a block diagram, you can make a rectangular circle at the center, right? That it is leaching operation. You have one feed and it contains certain amount of solute, remaining are inert, because according to us they are not taking part in anything. So we have let mole fraction of solute be xf. Then we have solvent. Solvent will not have your solute, so solvent will have a certain amount of kgs of thing. It may have certain amount of solute. Okay, that's different, because if you are recirculating, it may contain certain amount of solute. If it is fresh, it will be free from your solute. So we have two input, one is feed and another one is solvent. In both cases, let a mole fraction of solute of A, solute A in the feed be xf, the mole fraction of solute A in your solvent S is xs. Okay, and there are two output, as I said, overflow, let it be overflow be R kg of solutions. It may contain A and C, that is overflow will contain solute A and solvent C. Okay, and we are going to have a leaching underflow, in which it will contain some amount, all the inert will be present in it, as well as certain amount of solute. We may not be totally separating out your solute, right? So in that case, the underflow will have certain amount of A and inerts, all the inerts will be present in the thing. So that is the block diagram for leaching, and we can write material balance for overall material balance, and we have to write one individual material balance for solute. Inert material balance will help us to determine some of the values, because inert whatever is entering along with the feed will be present along with the underflow liquid. Okay, so that is also we are going to consider. When we do numericals on it, we will come to know that. Is leaching, and similar to leaching there is one more unit operation called liquid extraction. Liquid extraction refers to, so in leaching what we have done, we have a solid and one of the constituent solute A to be removed. For that what we have used is a solvent, right? So A plus B is your system, solid system, and C is your liquid solvent, right? So that is called leaching. Whereas in case of liquid extraction, you have a mixture of A and B constituents of liquid, and you are using the same solvent, third component solvent C, then that operation is called liquid extraction. That is, you have a liquid system, liquid mixture, and it has various components. Let me say I want to separate out A out of it. So what I will do is we will add a third component C into it, and A plus C will will form a mixture which can be easily, by density difference, we can separate it out by separating funnel or by gravity decanter, which you are studying in fluid mechanics. Gravity decanter is a large scale, because based on density difference, two liquid levels can be, two liquid streams can be separated out. That is called gravity decanter. In fluid mechanics Mechaber book you can read about it more. So such gravity decanters are used for large scale separation of two streams. Say for example petrol and water is there, they are immiscible in that case, so that we want to separate them out. So such gravity decanters are useful. So liquid extraction is an unit operation in which one of the constituents of a liquid solution is separated out by introducing a third solvent, third component solvent, and the solvent will selectively form a mixture with A, one of the constituent, and which will have a different density than the original solution. So from that way we can separate them out, and that is the other way, and after that A and B can be separated, that A plus C can be further separated. Okay, so here that is such operation is called liquid extraction. So here also we are going to have two inlet, similar to leaching. In leaching, feed is your solid. Here if you replace that feed is solid by feed is liquid, in that case this is called a liquid extraction. So obviously we have a feed stream with the solute A, and we are going to have a solvent which mostly may not consist of the solute, or if it is a recycled one, it may have some negligible amount of solute in it. Okay, so we have two inlet stream, one is feed of the liquid, another one is feed of the solvent. Okay, and what are the two outlet streams are? One is called raffinate stream, another one is called extract. Okay, raffinate stream and extract stream, two outlets are there, raffinate and extract. Okay, so we know what is the solute present in the raffinate, what is the amount of solute present in the extract. So these two input, two output. So your solute component will be present. We can write overall material balance, we can also write individual material balance for it. Okay, so that we can do for do the material balance for leaching, liquid extraction. So liquid extraction is similar to solid liquid extraction, which is leaching. Okay, solvent rich phase is called extract, and the solution from which the solute is removed is called raffinate. One of the most important unit operations in mass transfer is distillation. Distillation refers to an unit operation in which we separate out one of the components or few of the components from a mixture, liquid mixture, by vaporizing the components which have low boiling points. So when you have a mixture, it will have some components which have less boiling point. Less boiling point means what? It is more volatile. Which more volatile, when you say a person is more volatile means he will break down quickly, or he will get angry quickly, right? So, volatile, so they have the temperament will be like volatile. So so when you say more volatile component, which will have low boiling point, when you heat up to 50 degree or 60 degree Celsius, it gets vaporized, or if you heat up to 100 degree Celsius, water get vaporized. Some may have very high boiling point like 400 degree Celsius, 500 degree Celsius, so they are low boiling point, or they can say they are less volatile. So we have more volatile component A and less volatile component B, a mixture. So what we can do is we can use the difference in their boiling points or difference in their vapor pressures as the driving force. Okay, so as the principle. So what you can do is when two components are there, one having boiling point 100, one having a boiling point of 300, when we are heating the liquid mixture, when you heat up to 100 degree Celsius, what happens is A will get vaporized. A will get vaporized. So that way we get a bottom product which is free of A, or we may have very less amount of A present in it, but the vapor will be purely A, because when you want more purity, we can do for again and again such operation, right? So that such by using the difference in the vapor pressures as a concept, we do a unit operation called as distillation. So distillation is an unit operation in which we separate out one or more constituents from a liquid mixture using their difference in the boiling points or difference in the vapor pressure at given temperature and pressure. So that operation, it can be carried out in different ways. Okay, simple distillation is refers to, as the name says, simple distillation. Only we heat a mixture, and here also we can introduce a third component like steam can be introduced, because actually if it is a heat sensitive material or which may degrade when you are heating it to its boiling point. So in those cases, instead of actually heating to the boiling point of the one of the component, what we do is we introduce the steam into the system. So what happens, the steam plus that solute will form a new mixture which will have a boiling point less than that of water. That is, boiling point of water is 100 at 1 atmosphere. So this, when you introduce steam distillation, what happens is the boiling point of the mixture with the steam, solute A with steam, will be less than that of boiling point of water, which means that you are able to do the separation, that they will get distilled out. Okay, so vapor will be coming out. We are also, you are doing simply vaporization, we are getting collecting the residue at the bottom. Okay, so that vaporization we are bringing in is that one. Okay, so that is called distillation. Distillation can be simple distillation, steam distillation, or if you are introducing a third component into it, it can be called as extractive distillation. One of the component C, solvent C, like liquid extraction type, we can introduce one of the solvent into the system. So that way we can do extractive distillation. And also some of the cases azeotropes are being formed. Okay, so such distillation are called azeotropic distillation, and depending upon the pressure at which we are doing the distillation, it can be divided as atmospheric distillation, vacuum distillation, or high pressure distillation, like that. Okay, so this distillation unit operation also is part of your master answer course, so we will be learning it in detail about that. So essentially we are having a unit operation. If I have to make a block diagram of it, one box, I have a one feed stream. Okay, one feed stream, and we have one vapor at the top, a distillation product, we can say D as the distillate. At the top product is called distillate, the bottom product is called residue. So you can say overall material balance is feed equal to distillate plus residue, F equal to D plus W or R, whatever, F equal to D plus W or D plus R. So what is the mole fraction of solute in it? Obviously the solute will be present in all the three streams, that is feed, distillate, and residue. So we have to make an individual material balance for solute, so which will help us to solve the material balance problems in distillation. Okay, we will do some numericals on distillation also. Unit operation is absorption. In introduction lecture itself I have told you some of the unit operations are very important, even if it may not be giving benefit to the corporate owners or company owners, because these absorption towers are mostly used to filter out the SOx, NOx content that are present in the flue gases that are leaving the reactor or combustion chamber or gasification chambers or in steel industry, some the hot air ovens. Okay, so these flue gases will contain some SOx, NOx products, that is sulfur dioxide and nitrogen oxide products. So we have to separate them out. Even if it is containing ammonia, we have to separate it out. Okay, ammonia has to be absorbed. So what we do is we use a solvent. They are brought in contact with each other in counter current fashion or co-current fashion. The solute A, where I am talking about the pollutant A is solute. So solute A from the liquid gas mixture. From a gas mixture, we are introducing a liquid mixture into in counter current fashion. So the solute A will be dissolving into this liquid solvent. From a gas mixture, if so solute is dissolving into a liquid solvent, this is called absorption process. Okay, absorption is an unit operation which is used to dissolve one of the solute from a gaseous mixture into a liquid solvent. So how many input and how many outputs are there? There are two inputs and two outputs. There is one gas input and one liquid input. That is gaseous gas which is having the pollutant is having, that is the inlet. Okay, so you have solute concentration also in it. So solute is present in the gas entering the system, and you are having a liquid solvent. Mostly the liquid solvent will be free from the solute, or it may, if it is a recycled one, that liquid solvent will have negligible or very small amount of solute in it. So mole fraction of solute in it also needs to be known. So we have liquid stream entering the system, and there are two outputs. The gas after leaving the dissolving the solute from it to the liquid will be leaving the system. So a gas stream leaving the system will be less rich in A, because it has given off its solute A from its constituent. So one of the solute is going off along with the solvent, but it may not be complete removal. So there will be certain amount of solute present in the gas leaving the system. And another way, the liquid solvent is entered, no, it got rich in solute because it has absorbed a lot of solute in it. Okay, it also again depends upon various factors like solubility of solute. So because while choosing the solvent, we have to be careful. We should know the solubility. Less solvent, it should able to absorb more solute into it, right? So we have to choose it is compatibility also, and also it should be easily separatable and recover. We should able to recover the solvent again. Okay, it should not be toxic. Okay, it should not react, right? So like that we have decided properties that all we will learn in your master answer course. So here this absorption, in absorption this liquid entering will absorb more solute and leave with more amount of solute. So the concentration of solute in the liquid stream leaving will be higher than the concentration of solute present in the liquid entering the system, even it may be zero. What about in gas stream? The concentration of solute in the gas entering will be more, and the concentration of solute in the gas leaving the system will be less, because there is a loss of solute from gas to liquid. Okay, so this is the concept of absorption. So absorption can be carried out in co-current fashion, counter current fashion. So all these things we will learn. Even distillation and absorption are carried out in some packed towers where we have a packed material, and packed material will provide the contact between the gas and liquid, so that the effective mass transfer of solute from gas phase to liquid phase will take place. Okay, so here in this course we are going to do material balance for absorption operation. So there are three terms which we have to be familiar with in this particular course, that is bypass, recycle and purging. Bypass, recycle and purging. Now we'll see what is bypass. Okay, as the name mentions bypass, we can what we can do is in some cases as required, let me say, give you a case study. So actually we know a water purification system, RO, right? Reverse osmosis process, where we produce water, pure water. It will not contain any mineral in it. Okay, RO water will not contain major minerals in it. Minerals also will be completely removed. But they are, minerals are essential for our body, right? So what we do is actually the TDS present in total dissolved solids present in the RO water will be less than 20-30, but we should drink TDS amount of 70 to 75 is better. Okay, so that way the minerals present should be there, so that they help us to make us strong. Okay, so that way along with the product, so you have water entering the RO unit, and what we get is pure water, but that water is not good for drinking directly. So what we can do is we can bypass some water, or we can even mix. So the stream water entering can be split into two. The water that is coming out of pump, okay, we are taking out from bore well. So the power, so one portion of water is directly mixed with the product, so that we adjust the one composition, let me say the TDS amount, or the minerals present in water. That is one example of this bypassing is operation. Bypass is performed to uh, adjust the composition in the final product, because what we want to actually need is not attained in the system, or that obtained is too overqualified, or it may be underqualified, whatever case we have to adjust the composition in the product. So in that case, bypassing of a certain one particular stream, say for example 100 liters per hour is flowing in a pipe feed stream. Out of that 20 liters per hour we can take out and mix it with the final product. Only 80 liters per hour is processed. So whatever is the product that we obtain out of the system, so remaining 20 liters is mixed directly with it, so that we call bypassing. Another example of bypassing is this humidification, air conditioning. In air conditioning, in centralized air conditioning or air conditioning rooms, so what they do is the air conditioned air may not have the required humidity in it. Okay, so that way, in that case also, that what atmospheric air that is coming through the blower is mixed with it, and the final once we adjust the humidity, that air is sent into the closed rooms. Okay, so that is an example of bypassing. Okay, bypass streams. Okay, so that will be used in industries. Another term called recycle. Recycle refers to, say we are doing some operation at a particular very high temperature and pressure, but the conversion is not as expected. Okay, so that way the intermediate products formed are there, or whatever byproducts are there, but in some cases a portion of the product can be recycled into the system to improve the conversion. Okay, a portion of the product can be recycled into the system to improve the conversion, or to improve the purity if it is not chemical system. Okay, recycling is like a portion of the product is withdrawn and again sent back to the feed stream. It is mixed with the feed stream and sent back to the system. So that is called recycling. Okay, so we can say that with education also we can say bypass is like double promotion. There is one person has to move from first standard to second standard. Yes, bypassing means it is like a double promotion. Instead of studying first standard, he from UKG to second standard directly promoted. So it is bypassed. Okay, so that way it is bypass. That is example for bypass. Recycling means failing the students. Like for example, first standard, the student could not come and appear for the exam, so he is again sent back to first standard, and this is out of 50 students, 10 students are failed and again sent back to first standard. So that way, so that is what we are doing is recycling, recycle stream. Okay, recycling is different. Recycling, we call it like waste product is there, we make use of it for some other purpose, or for plastics or something things, we can recycle them and make again use it as raw material. Okay, so a recycle stream, where what we are talking is bypass stream and recycle stream. Okay, recycle streams, mostly when chemical reaction involved, we will be doing these recycle streams. But in that also there will be, when we are doing recycling of the unreacted products, there will be some inert component present in it. Okay, so we cannot have the product, sometimes the accumulation of the product in the system also is undesirable, or accumulation of the inert substances within the system also undesirable. So in that cases, to purge out, or we can blow down the products, or we can purge out the inert materials from the system. So what we are doing is a portion of the recycle stream. So we have seen, I said that from the product, one portion is taken as the final product and one portion is recycled back, right? So among the recycle stream, a certain fraction can be taken out periodically, or a certain amount has to be continuously separated out. So that is called purging. So this purging is important because we cannot allow the accumulation of some inert substances in it. For example, something is not taking part in the reaction among the feed that is entering, but when you are doing the recycling, it unnecessarily it will occupy the gas streams, the empty space into it, right? So that way we have to purge out a certain amount of recycle stream in the system. Similarly, in some cases we have to separate out the product that is formed also. For example, in ammonia production from nitrogen and hydrogen, certain ratio has to be maintained for getting ammonia. But if you are recycling in the recycle stream, certain amount of ammonia is being again and again circulated, no? So that has to be blow down. By cooling, we can remove the ammonia out of it, right? So that way some blow down operation or purging can be done. Purging, blow down can be done from the system. So, okay, so that way these three terms, what are they? Blow down and purge, recycling, bypass, these four terms are familiar and we should be aware of this. Okay, so we have to do calculation also for it, how much amount is purged out, how much is blow down, all this thing has to be done. Another simple unit operation that is being carried out in industries are mixing or blending. Okay, in different proportions we have to mix two liquid streams in a proper proportion. Okay, so that is called mixing. So this actually there will be heat of dissolution or heat of mixing will be there. So that and all we have to do in energy balance, we have to consider them. And with respect to this material balance of mixing is, so we will be having two liquid stream. Let me say concentrated solution. A is some particular concentration of A is present in a stream, fluid stream, and B is present in particular concentration in another stream, fluid stream, feed stream. So there are two feed streams. Let me say in one stream is containing some X percentage of solute A, and B stream is containing some Y percentage of solute B. Another it has in its solute, so another solute. Okay, so but we want to get a mixing of A this percentage. Let me, it is X percentage solution, that is Y percentage solution. I want a solution which contains X2 percentage of A and Y2 percentage of B. So that we want a blended product, just like how we mix it, right? Rasna we have to make, Rasna liquid is there, or Rasna powder is there, we have to get it in particular concentration. So similar to that, that acid solutions needs to be prepared, acid solutions will be prepared. So in a particular concentration, particularly when in nanotechnology, when we want to extract nanoparticles out of it, we want to do reflex and get fine particles. So for that, a mixture of sulfuric acid as well as nitric acid solution in 4 normal solutions I used to prepare. So that way when you mix the sulfuric acid and nitric acid mixture, so that will be used to do reflex or separating out the nanoparticles or cleaning the nanoparticle or activating the nanoparticle will be done. Okay, there's actually we are activating it or introducing defects into the system. Pure nanoparticles may not have absorb any material onto it. Okay, so it is important to introduce some hydroxyl groups onto it. So that way, so there and all we need a mixture of different acids, right? So that way that blending is required. So even as I in earlier case I was telling you, when you are doing bypassing or this thing, so what we have to do is we have to mix the water itself. So you have prepared more pure water, but what you want is some average pure water only you want. So what you can do is you can mix with raw water. That is one of the way of treating water also. So you say for example you have sometimes we have 10,000 liters of water. Okay, so it is having the pollutant present in it is slightly higher than the maximum permissible limit. So what happen if you are diluting the concentration by adding little amount of water to it, pure water without that pollutant, by mixing those water itself, we can bring down below the permissible limit, right? Say for example, some nitrate should not be more than 45 ppm in water. If it is around 46, so if I add a certain amount of water to it, I can bring down the concentration of the pollutant in water by below the permissible limit, which is safe to drink. Okay, so that way this blending of drinking water itself is an example for mixing. Okay, in industries there are several operations where you will be doing this mixing before, because we want a particular concentration. We have a 40% solution, but I want a some 20% solution, right? I have to dilute it, means we will be doing mixing. If we have to concentrate, it means we have seen what is evaporation. We have to evaporate out the solvent, right? So that way this mixing is an important unit operation which is widely used in industries. We are going to do material balance for it also. So only thing is, it is about concentration of solute A, solute B. If more solute are there, if only one solute is there, we have to do a overall material balance, and individual material balance are solute A. If there are 2-3 solutes are involved, we have to stream in which streams A is present, which streams B is present. So we have to write individual material balance for the constituents also. Okay, so we'll do some numericals on that. Another important material balance is dryer. Already we did some example problem for it also. So in dryer, what we will do is, we will have a solid material from which moisture has to be removed. So you will have a solid, dry solids, associated moisture will be present in it. So we will have input of solid material with moisture, and there will be output of solid with less moisture or minimum moisture or no moisture at all. Okay, 100% removal also possible. So that way we have one input of solid, one output of solid with its associated moisture, more moisture in the feed, less moisture in the product. And what we will be sending in is air. Air will be circulated into the system, and air will be picking up some of the moisture in it. So air with less moisture will be entering the system, and air with more moisture will be leaving the system. So that is the system of dryer. So in dryer, actually in cement industries, detergents industries, so all these places we have to dry the product. In pharmaceutical industries, drying is an important thing, because once the drugs are made, the powders are made, the moisture needs to be removed out of it. Okay, so drying is an important operation, unit operation carried out in industrial scale. Some industries may be having small scale, some industries will have large scale drying operations. Only the scale and size will be different, but drying is an essential part in most of the industries. So we will do a material balance. So there will be overall material balance, 2 input, 2 output, and for component also there will be, for moisture also we will write material balance. So individual material balance we will be writing for moisture. So moisture will be present in all 4 cases. So very rare cases dry air will be entering, because the only atmospheric air will be entering. So atmospheric air will have certain humidity, certain moisture content present in it. So obviously the individual material balance also, we will, for individual material balance for water, all it will be present in all 4 streams. So there are 4 streams, 2 input, 2 output, and in all 4 we will have moisture present in it. So that is the way we will be doing material balance problem for dryers. So if you make a block diagram for dryer, a circle or rectangle, so there is one feed, that is solids, feed solids or wet solid, and product is also solids with less moisture content in it, and another input is air with certain amount of moisture present in it is entering, and again there are another output is air is leaving with more moisture, because it is picking up moisture from the solid. The principles of drying, the rate of drying, all that we will be studying in mass transfer course. So in this course we are going to do material balance and energy balance in dryers. We will do numericals on it, that also. Okay, if you look at this unit operation, just a numerical one, abstract one. So there are 3 inputs and 3 outputs to this system. So there is one F1 stream, F2 stream, there is one S stream, there are 3 inputs, and there is a V stream, there is a P stream, and there is a W stream, and the mole fractions are given, XF1, XF2, XS, XV, XP, and XW respectively. So you practice the writing, how to write overall material balance and individual material balance for solute. So do it as an exercise. lecture we have discussed about material balance without chemical reactions, that is in unit operations at steady state, right? So among various unit operations we have seen absorption, we have seen distillation, we have seen evaporation, we have seen crystallization, we have seen mixing, we have seen leaching, we have seen liquid extraction. So these are some of the some of the unit operations in which no chemical reaction is involved. And we are going to do, we have seen how to write material balance, overall material balance and individual material balance for it. To sign off, once you complete lecture number 20 and 21, that is material balance, guidelines for doing material balance, how to choose basis, how to draw a block diagram, which basis to choose, what are the degrees of freedom, and what is purging, what is bypass, what is blow down, and what is bypass stream, what is recycling stream. Okay, so all these terms and various unit operations principles, how we have to write material balance, how many inlet stream, you make a table, you for each unit operation how many inlet streams are there, how many outlet streams are there, in how many inlet streams the solute is present, in how many outlet streams solute is present. All that if you make a summary table, we will be thorough with how many input and how many output, we will be able to solve the numericals on it. I will share some new practice numericals, we can solve them, and we will also try to solve them in the next lecture. Thanks for joining my classroom.